Hello everyone, we are from Group 6 and today we would like to present our project title Design of a Dual Band Microstrip Antenna for 2.5 GHz and 5.8 GHz Wi-Fi using GLC Studio Suite. This project focuses on design an efficient dual band antenna that works for Wi-Fi frequency and analyzing its performance using GST Studio simulation software. Our group consists of three members. My name is Muhammad Yusuf Habibi, and my study ID number 2211101041.
My name is Arif Wicaksana Markaputra with my student ID number 2211101074.
My name is Aurora Rutpati Sagala, and my student ID number is 2211101077.
We hope this presentation provides useful insight to the design and simulation of dual band microstrip antenna. Let us begin this presentation with the introduction section, which includes four main parts: background, problem formulation, objective, and theoretical foundation. 1. Background. The development of wireless communication technology has led to a growing need for fast and stable internet connection. Wi-Fi networks typically operate at 2.5 GHz for border coverage and at 5.8 GHz for higher speed. Therefore, a dual-band microstrip antenna is required to efficiently support both frequency bands. 2. Problem formulation. The study investigates how the use of slot loading in a rectangular microstrip patch antenna can achieve dual-band operation. Additionally, it evaluates how effective GLST Studio Suite is in simulating important design parameters at 2.5 GHz and 5.8 GHz. 3. Objective. The objective of this research is to understand the role of dual-band microstrip antenna operating at 2.5 GHz and 5.8 GHz in improving Wi-Fi performance by analyzing efficient antenna design methods and reviewing recent research. 4. Theoretical foundation. Microstrip antenna are now being compact, cost-effective, and suitable for dual-band use, especially when integrated with slot structures. FR4 is commonly used as the substrate. For good antenna performance, a return loss below minus 10 dB and a VSWR value below 2 are desired.
So, in the antenna design process, the first step is to determine the technical specification of the antenna. The target operating frequencies are 2.5 GHz and 5.8 GHz. The desired input impedance is 50 ohms, with a maximum voltage standing wave ratio of 1.5. The antenna is designed using a lossy FR4 substrate, and it is expected to produce a semi-omnidirectional or bidirectional radiation pattern. So these are the parameters that we use to design antenna microstrip with frequency 2.5 GHz and 5.8 GHz. This table presents the detailed design parameter used in the development of dual-band rectangular microstrip antenna. Each parameter plays a crucial role in shaping the antenna physical structure and performance characteristics. And the first parameters are width of ground plane for the value 44, length of ground plane with the value 41, height of substrate with the value 0.035, head of slot with a value 1.6, width of feed line with a value 3, length of feed line with a value 10, width of patch with a value 24, length of patch with a value 21, and then the last one are width with a value 5.5. So the result or the discussion of our project The first one are the antenna design. In this project, the microstrip antenna is designed using a rectangular patch structure modified with the addition of a horizontal rectangular slot at its center. And the purpose of this design is to enable the antenna to operate at two different frequencies, namely 2.5 GHz and 5 GHz, in accordance with existing Wi-Fi standard. And then the next part is the discussion about components antenna. The first component is rectangular patch. The patch is the main radiating element of the antenna, made of copper in a rectangular shape. Its dimensions are calculated based on resonance at the first frequency, 2.5 GHz. And the second one are rectangular slot. A horizontal rectangular slot is added to the patch to create a second resonant frequencies near 5 GHz. This load loading technique alters current flow, enabling dual band operations. The slot dimensions are carefully tuned to optimize performance at both 2.5, 2.4 GHz and 5 GHz. And then the third one are feed line. The feed line connects the RF source to the patch and is placed beneath it. Designed using the microstrip line feeding method, it ensures efficient power transfer and 50 ohms impedance matching. And the fourth is ground plane. The ground plane acts as a return path for the signal and stabilize the radiation pattern. Its size and position affect key parameters like return loss and resonant frequency. The last one are substrate. The substrate separates the patch from the feed line and influences bandwidth and impedance. This design uses FR4 due to its affordability and suitability for Wi-Fi. And then the next part are about S parameter. From the simulation result, we can see that the antenna has two clear resonance points at 2.5 GHz and 5.8 GHz, with S parameter values of minus 34.6 dB and minus 17 dB respectively. These values indicate that the antenna has very good impedance matching. The meaning are very little power is reflected back to the source and most of it is radiated efficiently. At 2.5 GHz, the return loss is extremely low, which show excellent matching and high radiation efficiency. This make it ideal for Wi-Fi in the 2.5 GHz band. The second resonance occurs at 5.8 GHz. Even though the return loss here is not as low as the first, it is still within a acceptable limit below minus 10 dB, which means the antenna performs well in the 5 GHz Wi-Fi band. So overall, this antenna is confirmed to work effectively at both frequency bands, making it a reliable dual band antenna. It offers flexibility and high performance for modern wireless applications that require both wide coverage and fast data transfer.
Discussion 1. Return loss. Here, the antenna achieves optimal performance with a return loss of negative 34.615 decibel at 2.566 GHz and negative 17.06 decibel at 5.8361 GHz. These values indicate excellent impedance matching and minimal signal reflections. This confirms that the antenna is effective for dual-band Wi-Fi operation at 2.4 and 5 GHz frequencies. Next, VSWR values are 1.38 at 2.5437 GHz and 1.33 at 5.8361 GHz. This show great impedance matching, allowing power to B transmits efficiency with very little reflections. This law VSWR follows proof that the antenna design is well optimized in terms of patch size, substrate material, and fitting methods. Next, far fields. This section shows the radiation pattern of the antenna at 2.5 GHz. The pattern is broader, which is ideal for indoor Wi-Fi coverage. At 5.8 GHz, the radiation becomes more directional, giving better signal focus. This semi-omnidirectional radiation pattern proves the antenna is well designed for dual band Wi-Fi. Next, conclusion. The rectangular dual band microstrip antenna designed with GST software performs successful at 2.566 GHz and 5.836 GHz. This is proven by excellent return loss and VSWR values. Its structure, which includes a horizontal slot and FR4 substrates, support good impedance matching and efficient signal transmission. The radiation pattern, both omnidirectional and directional, makes it suitable for modern Wi-Fi application.
So I think that's all about this project. Thank you.